right, so now we're back and we're going to talk about second order conditions when we have more than one variable that we're trying to find as optimal values. So in this case, what we're going to look at is a two-dimensional relationship between the input x's and the value, the function of the x's. And we're going to look at something called a Hessian. Hessian? I don't know, I'm going to call it a Hessian because that's the word I like to use. Right. So here we have a Hessian. And so first of all, we found the gradient, the first derivative of the equation with respect to x. So that value is df with respect to x. And this value here is df with respect to the y. All right, so this is a 2-by-1 matrix or vector. And so the Hessian looks at the derivatives of our first derivative, the second derivatives and the cross products. So in this case, we're going to have the Hessian of f is going to be the derivative, second derivative of f with respect to x squared. The second derivative of f with respect to x times with respect to y, the cross product. All right, so it's going to be both. We're going to look at the relationship, this first derivative, and then we're going to look at the second equation, the derivative of f with respect to dy crossed with dx, I should say, and the second derivative of f with respect to y squared. All right, so first of all, we take our first equation. And here we have our x's and y. So we got an x here and a y there. So let's take a look at this. All right, so we have the derivative of this yellow line with respect to x is going to be negative 72. The derivative of this yellow line with respect to y is negative 5. The derivative of the second row with respect to x is going to be negative 5. And the derivative of the second row with respect to y is negative 32. Now, the rule here is we want this Hessian to be kind of like the equivalent of a negative derivative. So we want this Hessian to be something called negative definite. And so the negative definite rule is if we take the principal minors or the determinants of a 1-by-1, 2-by-2, 3-by-3, 4-by-4, however big this dimension gets, and we alternate between negative, positive, etc., we got ourselves a negative definite variable or matrix. But if all the principal minors are positive, we get a positive definite, which is the multivariate equivalent of a positive second derivative. We get a minimum. All right, so let's take a look at these principal minors. We take the determinant of this principal minor there. Well, it's just a scalar, so that's equal to negative 72, which is 0. So if we take the derivative of the second principal minor, which is the entire matrix, it's going to be the derivative. It's going to be negative 72 times negative 32 minus 25. And that, I believe, equals 2,279, which is positive. So we have this negative positive relationship. So this Hessian is negative definite. So this is the sufficient condition for a maximum. So we're not always going to check these things in our class. Yeah, I guess we will once or twice, but all we're trying to do here is set first order conditions equal to 0, solve for the portfolio weights or something like that, and then every now and then, I guess for completeness, we want to check to see if the second derivative conditions, second order conditions hold. All right, so I think that's all we're going to do on this slide, set a video, and we're going to have a finance application coming up.